This feels a bit schizophrenic. We're almost back to the first session again, which is on environmental issues. And we have three speakers, one of which is an honorary person from the room, who's not in the room, but seems to have been around us all the time from the beginning of the conference. And that's Dan Hawke from the, can't remember your association, Dan, you'll have to remind me when you start. And we have Andy Williams talking about dark sky and Benjamin Winkel from the Max Planck Institute for Radio Astronomy talking about radio issues as well. So let's get a move on with this. We have three speakers, about 15 minutes each, everyone, yeah? And we'll start with Dan. Do you want to just introduce yourself, Dan? Hello? You're muted, Dan. Dan, this is the first time you've been muted all through this. Oh, Dan, your microphone isn't working. So maybe we could move to Andy. Dan, maybe you could look at sorting your microphone out. And we can start with Andy. Are you okay, Andy, to start now?
Yes, of course. So
thank you very much.
Me just share my screen here.
Andy, I'll give you a sign after 10 minutes, right?
Okay. Share. Okay, so can you confirm you can see and hear me?
Yep.
Okay, fantastic. So good afternoon, everyone. My name is Andy Williams, and I am ESO's External Relations Officer. So just in case you don't know, ESO is an intergovernmental organization for ground-based astronomy, 16 European member states, of which the UK is, of course, a key member. And I'm also here with a second hat as co-lead of the policy hub of a new International Astronomical Union Centre, about which I'll talk later. And I'm here with my co-authors, Olivier Hainaut, who did the simulations for this talk. He's not here today, though. Paola Nunes-Tatari, she's online here, working with me in external relations. And then my other co-lead of the IAU Centre, Richard Green, from the University of Arizona, who also unfortunately couldn't join it. So this session is about the environment. It's about preserving it, the night sky, and how we can work together. But I'm going to start with a quick summary of impacts on one particular field, which is that of ground-based astronomy. And then I'll talk about some of the actions that we're taking in this regard. So there are many reasons to preserve the night sky, and this is just one of them. The fact that 16 European states are bound by an international treaty as ESO to deliver world-leading astronomical instruments. This is a substantial public investment, so it's important that we are looking out to the future and we're identifying any risks to our operations. So this is our next project, the Extremely Large Telescope. I mean, it's a multi-generational project. It's going to be there out to the 2060s and probably 2070s. And the ELT will be a JWST-like revolution in astronomy because of its huge light collecting power of its telescope. It's a 39-meter main mirror. But unlike the James Webb Space Telescope, which is 1 million miles from Earth, we are on the ground looking up at space through the environment into low Earth orbit. So we care about this environment. And just for your interest, this is what it currently looks like. So it's a project that's really in construction. Okay, so now we're talking about constellations. If we look at the major planned telecoms constellations, we see that several projects are underway with launches and construction. And there's some quite amazing figures. So the filing by the company eSpace, for example, is planning for 337,000 satellites in low Earth orbit. And when we include all the constellations, we can reach some quite amazing numbers. Yeah, so 426,000 satellites in the region of Leo. And I'm sure that this community is well aware of all the potential problematic issues there. Now, we know that many of these systems, may not actually be launched in the end, but given that the lifetime of an observatory is very long, as I've just mentioned, often 30 or 40 years, we need to plan long term. So the impacts of this growth in satellites, well, I'm sure you've seen images like this before in the media. They give really a qualitative sense of the problem. And we have, over the past few years, trying to quantify the impact of this on our science. So I hope I can offer a flavor of this impact. And just to mention that it's not just ground-based telescopes, it's also space-based telescopes in low Earth orbit that are going to face problems. So here are some images captured by the Hubble Space Telescope of Starlinks and defunct rocket bodies. And it's also affecting radio astronomy, which I'm not going to talk about because Benjamin later will have a specific talk on that. But the radio environment for astronomy is going to change substantially in the coming years. Okay, so let's go back to the ground now and imagine that we are standing on the mountaintop of ESO's Paranal Observatory on the VLT, and you look up, and this is what you see. This is a 360-degree view of the night sky. So the sun is setting over there on the right-hand side in the west, and on the east side, it's dark. And I draw your attention to this dark arc that's stretching from top to bottom. This is the shadow of the Earth on the sky. And of course, there are satellites that are present all the time overhead. But if they're in the shadow region, then we won't see them in an optical sense. Of course, for a radio telescope, that's another matter. So for the astronomers planning observations, you want to know, where are the satellites? Can you avoid them? And if you can't avoid them, what's the impact? So we can make some simulations here. And this is what I will quickly show you. We can make a sort of satellite weather map. So what we are looking at here, this is the 360-degree kind of fisheye view of the total night sky. So the center is roughly vertically up, and then the edges of the circle are on the horizon. And this is showing the impact on ESO's very large telescope, which is the one that's there at the moment in existence. And the green color means that less than 0.001% loss of image, while the red color, this is about 10% or more of exposures are lost. So we can look at three cases. So the first one is the situation today. So about 4,500 satellites in low Earth orbit. And we can see that, it's mostly green. So this is very few images lost. And now let's look at the second and the third image here. So the middle one, this is the full SpaceX Starlink constellation simulated, so 42,000 satellites. And then the one on the right here is a fictional high altitude constellation, which is actually basically just the Starlink constellation, but raised up to above 1,300 kilometers. So for the real Starlink, this is the one in the middle, the effects are really confined in this area towards the horizon. And you can see that the shadow area is quite large. And this is because the Starlink constellation, it's quite low in altitude. So the satellites spend less time illuminated by the sun. But you can see that there's this band of orange and red towards the horizon. So for telescopes that look very close to the horizon, this will be a problem. And that's actually not the case with the VLT, because we don't really look below 20 degrees. Now, for the high altitude constellations, this is on the right, you can see that the effect is much worse. So we've got a larger affected area of the sky. It's more red, it's more yellow. And this is because the geometry of the situation is that higher altitude satellites spend less time in the shadow, more time illuminated by the sun. And they also move slower across the sky, as seen by the telescope. They have more time, in effect, to deposit their photons into the telescope, and they're actually more in focus to the telescope, which makes the problem worse. So now for ESO's very large telescope, which in general is actually one of the least affected types of telescopes, we're now talking about a 2 to 10% loss of images, and this would really start to have an impact on our operations. Now, as I've said, the VLT is a narrow field telescope. It sees only a tiny portion of the sky. The situation is quite bad for telescopes that see a large portion of the sky. So the Vera Rubin Observatory, for example, is currently in construction in Chile and its final stages. And the simulations here are showing a 30 to 100% loss of images in certain regions. And there's a paper which was just released recently, and they've looked at what to do, and one approach to reduce the number of streaks by a factor of 2 is to basically lose 10% of the observing time. And considering that this facility is a 10-year lifetime cost of about $1 billion, I mean, 10% is quite an impact of that.
5 minutes, Andy.
So thank you. Yeah. So let's go back to our beautiful night sky. And I mentioned this number of 400,000 satellites as per the ITU filings. So now we're quite skeptical that that's actually going to be the case, but let's consider what actually happens. And this is if we run the simulations for the VLT, and it also would apply to the ELT. It's about the same. And here we see that now, essentially half the sky, every single image will have one or more satellite trails, and between 10 and 100% of images in this region are lost. So this really underlines the importance to work on mitigations, think about the long-term situation. So just to summarize the impacts here, so we're concerned about the overall number. So the more satellites there are, the worse the impact. We're concerned about the altitude of these satellites, and in general, the lower the constellation is, the better, and they spend less time illuminated. But of course, that then has other effects, on space crowding, etc. And then we're concerned about the brightness. In general, we want the satellites to be dimmer, ideally such that you can't see them with the naked eye. So this visual magnitude limit of 7. We're also thinking about what's coming in the future. It's not just satellite constellations. So here are some things at the top, important measures for low Earth orbit sustainability, the passive deorbiting drag sails, and important things for sustainability on Earth, the space-based solar power projects. But, these are potentially very bright objects. And from the astronomy point of view, we want to understand this. And then this image at the bottom, this is the AST mobile, which was recently unfurled in space, this giant 64-meter squared antenna. And it's that large because it's aiming to talk directly to your cell phone rather than going through a ground station. So this is something that we're monitoring very closely. And of course, it's not just this company. Now SpaceX are starting to look at how they can do this with Starlink and make the platforms much bigger. So what are we doing about this? Well, we are working very closely with the operators, and SpaceX are one of the leaders here. In fact, they've recently published a very nice paper kind of capturing and describing their various mitigations. And their latest approach is to put a new type of mirror coating, which basically creates a specular reflection and reflects all the light off in one direction, in combination with some new types of black paints and operational adjustments. We're also in collaboration with Kuiper, with OneWeb. We've had some initial contacts now with AST Mobile, and they are also considering other types of mitigations. So we can say, okay, good, productive, voluntary bilateral collaborations are established. This is great. In many cases, it's under a non-disclosure agreement. Okay, fine, but that doesn't allow the knowledge to be shared. But at the sort of basic problem is that there's nothing compelling the operators to do anything. There's zero regulation effectively about the brightness question. So to sort of close out, what are we doing? Well, the International Astronomical Union, as I've mentioned, and now I'm putting my second hat on as co-lead of this new center. So we're taking some actions at COPUS, the Committee on the Peaceable Uses of Outer Space, and we've recently established this IAU center, the Center for the Protection of the Dark and Quiet Skies from Satellite Constellation Interference. That's a bit of a mouthful, so let's just say CPS. And the center is aiming to continue research to bring together astronomers with all the other stakeholders involved, with industry, and act as a bridge between them, and to try and coordinate our actions together, sort of get over this problem of multiple bilateral different agreements with all the different companies, and then share various information about this. So it's hosted by NOAA out of the US and the Square Kilometre Array Observatory, which is another intergovernmental organization building the world's largest radio telescope. And it's organized into 4 hubs. So quickly describing them, we have a SAT hub, which is providing resources for astronomers. We have a community engagement hub, which is aiming to outreach to the broader community. We have a industry and technology hub, which I'm pleased to say is chaired by someone from Amazon Kuiper. And we're working on bringing more operators into this. We're developing a sort of Astronomy 101 document and then an Industry 101 document to help the communities talk. And then finally, where I'm personally involved in is the Policy Hub. So we're supporting the EPFL Institute in developing an astronomy module of their space sustainability rating and looking to coordinate various policy actions across the community. So that is the IAU Hub in a nutshell. And to conclude, feel free to take your mobile phone and take a picture, and it should take you straight to the link where you can get some more information. And you're also welcome to join us. There's a form online that you can put your email in to be informed of our activities or even contribute to our work. And, this is something that we need to continue. We're norm building at the moment. We've got this cooperation with industry. This is good. We need to work on the international dialogue, which we're doing at COPUS. But my closing point is that, all this is great, but I think at the end of the day, there's a real environmental problem here about the space environment, the impacts of space activities, and the aggregate effects. It's not just one system, it's the combination of all of them that really causes the problem. And this is a very difficult situation to solve. So we need to have some kind of government intervention. So on that note, I will close and thank you very much for your attention, and I'm happy to take any questions later on. So thank you.
I don't know if we'll be able to do questions now. I don't know if we'll be able to do questions after the minister. No? Okay, well, let's just see. So if you can hang around, Andy, just in case. So we have to move on. We've got 2 talks to do for 4 o'clock because we've got the science minister going to address the conference at that time. So who do we have? Dan, can you talk?
Can you hear me now?
Yes, we can hear you. Can we share your screen? So Dan, I have to say, can you do your talk in 12.5 minutes?
I can.
You can. Good man.
I will share my screen. I'll share my screen here for a second.
Dan, at 10 minutes, I'll give you a warning, right?
All right, sounds good. All right, can you hear my slide? Can you see my slides?
Yep.
Okay, so again, my name is Dan Hawk. I'm Oneida. I'm Native American for the United States, Iroquois Confederacy. I am going to go through 6 slides relatively fast. And what's important about this slide is the red writing on the right, is Think Inyan. And Think Inyan, from my point of view, is how we need to think indigenously, a different way of thinking when we talk about space, we talk about our environments, how we go about doing things as Native Americans are caretakers. So we're caretakers of our land, caretakers of our water, caretakers of our ocean, caretakers of our space and our air, and caretakers of the moon. The idea is that everything we do is connected. So what we do today is connected for tomorrow. The things that we do now are connected to things down the road. We need to think a little bit differently, and that's where the thinking in comes from. And the Iroquois legend for our Oneida people is that we come from Sky World, and here are 4 pictures, graphics that show that our creation story is from Sky World. This is where we lived. This is where we came from. This is who we are. So you can imagine how we feel when we talk about orbital space debris, those things that when we look up into the night sky, how they affect and impact us from the beginning of time for us. It's very emotional. And so when if you were to just look up satellite pollution, this is the very first picture that came up about. It may not, it's not accurate, of course. It gives you an idea, an understanding of what satellite pollution would do in our orbital space. So
Dan, your slides aren't moving. So if you want to move your slides, we're stuck on your first slide still, Dan.
Okay, so let me see.
Try again, yeah.
I'm stopping sharing. I'm going to go to the next slide manually. Can you see this?
Okay.
Can you see the Skyworlds slide?
No, we can only see you now. You need to share your screen.
All right, I will go back to sharing screen. And I will leave that open. Are you able to see the second slide?
We can see it. We can see it sufficiently now, yeah.
Okay, I'll make it larger. I can.
Yeah.
I will leave the slides up on the left-hand side just in case that's what I need to do. So here again, here's the pictures depicting the sky world of where we came from, our creation story, how we live, how we go about understanding our orbital space, our sky. And so the Iroquois legends, this is Sky World. And then if you were to, like I mentioned before, if you were to look up what satellite pollution would be, this is the photograph, this is the picture that you would get, this is the depiction that you would get of our orbital space debris and how that impacts us as indigenous people, how we go about understanding our orbital space. Even though we can't see it, we are starting to see the effects of satellite trails, the reflections that we have been talking about since yesterday. And so here is that kind of information that we were talking about. These lines, these streaks, these constellations, these strings of satellites impact how we think about our orbital space, our sky world, that we are, as an indigenous people, how we go about looking at our indigenous ways of knowing. We used to navigate by stars, plant by the stars, plant by the moon, plant by our astronomy capability as indigenous people. Now, this is going from that. On the left-hand side, the new face of space is we are indigenous people. We are the new face of space. We are going to space. We're talking about this in an indigenous world situation. We talk about the collaboration of spacefaring countries and larger countries, but we don't talk about the collaboration of indigenous people, and that's what we need to do. So what we love, we love the sun, we love the moon, we love the stars. So this is who we are. And then on the right hand side, you have a native girl that says, I want to be an astronaut, the new face of space, right? We are the new face of space. We want to be astronauts, but we're going into space. The United Nations says that, to indigenous people, you have an equal access right to space. It is a human right to go to space. It is a right of self-determination to go to space. This is for world indigenous people, not just Native Americans. But we go into space at a time where we have a lot of orbital debris, and it's going to get worse. And so here you have this young girl that wants to be an astronaut, but at a time where we are looking at problems of orbital debris that can impact human space flight. And so it's difficult to say, but we're going into space. We want to go there, but we know there's greater dangers at a time when that should not happen. We should not be having that debris. We should not be having this conversation about orbital space debris. We didn't do it right, and that's part of the issue of Western thought, again, as compared to indigenous thinking. My last slide is, so what are we going to do about it? So what are we going to do about it as indigenous people? Well, first, The first thing we did is we partnered with NASA through all the NASA centers, and we have now the ability to have tribal interns in NASA for all of the NASA centers for all different kinds of things. On the left-hand side is our first space engine test chamber. And we talked, yesterday, Newman Space talked about the idea of what do we need to do to have active debris removal, and that has to do with the key is propulsion. And for us, we're looking at interstellar propulsion. We're looking at a propulsion that would be able to take orbital debris and over many attachments to ADR and be able to take those debris and deorbit them and put them into a deorbit procedure and have them burn them over the ocean, which we're not exactly happy about either. But the point is that if we're going to move orbital debris, we have to have the propulsion capability to do it. And that is what we're working on. We're working on that ability to do that. So that is our solution to this problem of orbital space debris. And I guess that's what I would like to say. And I'll be able to take questions at the end.
Dan, I'd like to thank you for keeping to time on this, or even being faster. I can't imagine what it was like, maybe even 100 years ago, as Western civilization was spreading towards your people and the threats that they must have felt at that time. And this is like another threat. That is not just your threat, it's our threat as well. Anyway, hopefully we can come back after the minister. So can we move on to Benjamin? Sorry, Benjamin, you've got 13 minutes. So at 10
try
minutes,
my best.
Good man, Benjamin.
Okay, let me share my screen. Hello, everyone. Thanks a lot for having me here. I'm in the lucky position that Andrew Williams was already talking about the general problem of satellite constellations and astronomy, so I can focus a bit on radio astronomy. And you see here my co-authors, Gyula Joja, who's also with you in the room, so feel free to catch him and ask questions, and Federico Di Bruno from the CBS and SKO. So I'll talk briefly about radio astronomy. I can assume that not all of you know a lot about radio astronomy. And then I would like to say why radio astronomy is also affected from satellite constellations, and give you a little introduction into the existing regulatory framework and the coordination that we can do in the radio. Okay, first part, radio astronomy. So why do we do radio astronomy? And you see here two very nice pictures. On the left, you see an optical image of the night sky showing a couple of galaxies. And on the right, you see a radio image where we mapped the neutral atomic hydrogen. And you can see they have not much in common. You see the galaxies, but in the radio image, you see a lot of stuff between the galaxies too. And in fact, this is gas that is ripped out of the galactic disks by gravitational forces. So one can really say that the radio astronomy regime opens an entirely new window into the universe. And there are plenty of examples that where you really need a multi-wavelengths approach in astronomy to get the full picture of what's going on there. And I don't really have time to show you a lot of our interesting results, but you probably have seen this iconic image of the black holes in our own galaxy and in M87 in the news. This is also radio astronomy, just to let you know. Okay, so how do we do all that? It's good to start from the understanding that the cosmic signals in the radio domain are extremely weak. For example, put a cell phone on the moon, it would be among the brightest signals on the sky. And in order to really get all these weak signals, we need huge detectors, huge collecting areas. And that's why we built single dishes up to 100 meter of diameter size. And on the other end, we also combine many different telescopes. For example, the new square kilometer array that is under construction will have 1 square kilometer collecting area. And we also cool our receivers to get the electronic noise down. So the typical receivers are maybe cooled down to 20 kelvins, which is minus 250 degrees Celsius. We operate with bandwidths up to several gigahertz, and that all of that combined allows us to observe with sensitivities like this. So we even introduced a new unit, the Jansky. 1 Jansky is 10 to the minus 26 watt per square meters and hertz. And I think that demonstrates already that we are extremely vulnerable to human-made transmissions. And in fact, I can show you an example. This was measured by a colleague of mine some years ago at our observatory. This shows you the radio spectrum between 500 megahertz and 3 gigahertz. And it's full of human-made transmissions. We all use this in our day-to-day life. I mean, GSM is not in operation anymore, but of course, we now have 5G and stuff like this. So this already shows you that radio astronomy is having difficulties since long time with the radio spectrum. And of course, this doesn't stop for satellites. And likewise, with satellites and radio astronomy, this is not a new thing. This figure here shows the Iridium satellite signal. Iridium is a communication satellite system that is up there for about 30 years, I'd say. And from the beginning, it was really bright for radio astronomers. Just to give you an idea, an astronomical signal, which is extremely, which is one of the brightest that you would get at this frequency. Usually we observe much less bright signals there. This is a tiny blip here compared to the satellite signal. But Iridium had a different problem also. It's not only that Iridium operates in their own frequencies, but unfortunately, they also produce what we call unwanted spectral side lobes, so signals leaking to different frequencies above and below their carrier signal. And unfortunately, we were in the unlucky position that some of this leakage made it right into our own radio astronomy frequency interval. So you see here that we get signals in our observing band. And that also is there for the last 30 years or so and creates interference for our data. Okay, another thing that I can mention is satellites, when they have very bright transmitters, for example, SAR radars that are used to map the Earth, they could even damage our receiver. They are so powerful that our low noise amplifiers could break. And to avoid this, they have to be shut off when they go over one of our telescopes. And this is handled by the ITUR. And that brings me already to the final part of the talk, where I will explain a little bit how the regulatory framework, how that works and how we coordinate. Now, for the spectrum, the International Telecommunication Union is responsible. They publish the radio regulations, and the radio regulations, they define all these rules and principles, and at the core of this is the frequency allocation table. So the frequency allocation table has entries for every frequency in the radio spectrum and which service is able to operate there. And to visualize this, I show you a nice map of the which was made by the United States, showing their frequency allocations, but it's very similar in other countries too. We have to zoom in to actually see something. So this is just a tiny bit of the allocations between 1300 megahertz and 1850 megahertz. And you see whoa, every single hertz of the spectrum is actually allocated to a service. And many of the slots here are actually allocated to multiple services. And radio astronomy has some allocations too, but this also shows that, well, without coordination, nothing is going to happen there, because it's easy to imagine that different services might interfere with each other if this is not done correctly. And that's why there is a lot of need for coordination, and this is done by compatibility calculations, for example. So you actually study how much power would be transmitted by a given service, by an antenna of one service, and you want to know how much another service, another antenna would see this signal. And this involves the calculation of the loss along the propagation path. This is actually what we do on a day-to-day business in the ITU. And it's the same for satellites. You just follow this recipe. Of course, there are more complex details, but the principle is quite simple, actually. The only thing is, for satellite, of course, you have to sum over all these satellites, because everyone would contribute to the power that you see at the receiver. Now, when you do that, you can actually simulate full satellite constellations and calculate how much power you get from a full constellation. When you, for example, take your radio telescope and point at a certain position in the sky. So this shows you each pointing position of a radio telescope and how much power you would see from that at that position. And it doesn't stop there, because satellite constellations also have a ground component, right? They use gateways to communicate to the internet, but they also have user terminals. So you also have to do calculations for the user terminals. And this is one example for the Starlink system around the Effelsberg station in Germany, which shows in which areas you cannot use a Starlink terminal unless you want to interfere with our observations. And that brings me almost to the end. Let me quickly summarize some of the protection measures that you can actually have to have proper coexistence between different services. So the first one is actually quite simple. You somehow need to get the received power at your radio astronomy observatory below a given threshold. And that usually means that you should avoid spectrum sharing. So if we would wanted to observe at a frequency that is actively used by a satellite system, I don't think that would ever work. But we can easily separate the frequency bands on which we operate. So, and if we are in a frequency adjacent to the carrier signals of a constellation, we just have to make sure that there's sufficient filtering of the out-of-band signals so that we are not affected, or we use guard bands. What also helps is if the satellites have as small as possible footprints on the ground, because this allows us to use some geographical discrimination. On a side note, one should also try to avoid that too much power goes into the radio astronomy receivers, because that could lead actually to damage, as I explained earlier. Or if it's a milder case, it could lead to harmonics and intermodulation products in the radio astronomy receiver. So bottom line is, one should also avoid direct illumination of radio telescopes if possible. And in practice, in Europe, we are in the lucky position that much of this was actually implemented. So already 5 or 6 years ago, the European Conference of Postal and Telecommunication Administrations, so Spectrum Agency of Europe, if you will, published ECC report 271. And there we studied Starlink and OneWeb versus a number of victim radio services. And one of these radio services was radio astronomy. And it was this report that really figured out, well, there will be a guard band needed between OneWeb, SpaceX, and radio astronomy. And Otherwise, we are good. The out-of-band power is then sufficiently low to not affect the radio observations in the adjacent frequency. We also determined how large the exclusion zones for the terrestrial user terminals would have to be. And we made a study about this intermodulation product thing that I mentioned a minute ago. Unfortunately, the consequence to avoid direct illumination of the radio telescope has so far only been implemented in 3 European countries, which is Germany, Spain, and Italy. And we are really thankful to the administrations of these countries for doing that. I have to say, this does not mean that we will be able to observe at the satellite frequencies. We will only be able to observe at our own frequencies by implementing this. So the fact that they don't illuminate the radio telescope doesn't mean that we get more frequencies for our access. No, it just means that we can observe at our own frequencies. Okay, so I will leave the summary on screen and stop here because I'm already taking the minister's time. Sorry for that.
Thanks, Ben. Benjamin, much appreciated. And thanks for talking about Starlink as well. So without further ado, over to Catherine to introduce the minister.
And thanks to the to those speakers. If you can hang on and take some questions later, that would be great. If not, I understand and just want to say thank you very much for those talks.